Hi, and welcome back to Understanding Motors. This episode, we're going to talk about using motors as generators, and we're going to start off by asking a question. Let's say you drive a state-of-the-art electric vehicle, which uses regenerative braking, and you only drive at low speeds and you never slam on the brakes. But then one day you bring it into the mechanic for its routine servicing, and the mechanic tells you that you need to replace your brake pads. And that gets you wondering, why in the world are your brake pads getting worn out? Shouldn't your car be converting all the kinetic energy back into recharging your batteries? Isn't it decreasing its efficiency by using your mechanical brakes anytime it doesn't have to? Well, this episode, we're going to discover the surprising answer to this question. But first, we have to talk about some basic concepts of regeneration. So, let's get into it. This episode, we're going to talk about a couple of ideas which we'll use to approach the question of a car's braking. First, we're going to talk about what regeneration is and the two primary ways in which it can be performed. Next, we're going to talk about a key idea that's frequently forgotten when talking about regeneration: torque production. And finally, we'll tie all of this information together to discuss the question of regenerative braking we posed in the opening. So, let's start our discussion of regeneration with the basics: what it is and how it works. As you likely know, the key idea of generation is that we're using a motor to convert kinetic energy into electrical energy. It could be argued that regeneration is any instance where current and thus electrical power flows back into the supply. However, this would include things such as the unforced phase of hard switching, abrupt changes in current commands, and ultra-high-speed commutation, where the regeneration is not the goal, but rather just a side effect. So for the purposes of this video specifically, we're only going to look at situations where regeneration is the primary goal, not just a secondary result. In such situations, the key to converting mechanical power into the electrical domain is the back EMF generated by spinning the motor. As we've discussed a couple of times in this series, the back EMF is a voltage potential generated due to the motor coils rotating in its magnetic field, and it is approximately equal to the motor's torque constant multiplied by its angular velocity, assuming you have your units in check. If this back EMF is greater than the voltage supplied to the motor, then the net voltage on the system will drive current up from ground back into the supply. If your motor is connected to a battery, this would begin to recharge your battery. So that's the general idea. But let's do some analysis and try to quantify this a bit. First off, how much of the power into the system is being converted into electrical energy? Well, we know that the mechanical power in a rotational system is equal to the torque times the angular velocity. So, the power flowing into the motor system from the external world will be equal to the rotation rate of the motor multiplied by the torque. What the rotation rate is pretty obvious, but this torque in the motor actually has two terms. The first is the frictional torque, which only goes to producing heat. The second is the torque due to current flowing in the motor. And of the two torques, only the power associated with this term is actually available to the motor's electrical system. As we've said before, this electromechanical torque from the motor is approximately equal to the motor's torque constant multiplied by the current running through the motor. So that's the power into the system. Now let's set these equations off to the side for a second and think about the motor's electrical system. As we know, electrical power is equal to current times voltage. So what's the power flowing back into our supply? Well, our voltage term will be equal to the supply voltage, and our current will be the net voltage divided by the impedance. For our analysis here, we're going to ignore any frequency components of this and simplify our impedance to just the electrical resistance of the system. So now our power out of the motor into our supply would be equal to our supply voltage times the difference between the back EMF and the supply voltage, all divided by the resistance of the system. There's a couple of key ideas that I want you to take away from this analysis. First of all, since real-world systems all have losses to friction on the mechanical end and resistance on the electrical end, we can say with certainty that the power flowing back into the supply will always be less than the power being put in on the mechanical side. Another way to say this is that in real systems, generation cannot be 100% efficient. We also notice that for a fixed supply voltage, our current flowing in the electrical system is strictly a function of the back EMF and thus the rotation rate of the motor. The implications of this are twofold. First, on the mechanical side, the electromechanical torque that the motor is applying back on the system is proportional to the current running through the motor. Substituting our equation for current, we thus see that when the motor is used as a generator, the resistive torque on the mechanical system will be linear with angular velocity of the motor. So, from the mechanical system's perspective, the motor sort of looks like a viscous damper. We're going to come back to this idea of torque in just a few minutes. But first, on the electrical front, the current being linear with angular velocity means that the amount of energy the motor is regenerating is dependent primarily on the rotation rate of the motor. And you will notice that if the motor is rotating below a certain rate, namely the supply voltage divided by the torque constant, it won't be able to force any current back into the supply. Well, depending on what your supply voltage is and your motor's characteristics, that can be a pretty huge constraint to generation. Luckily, however, by leveraging the motor's inductive properties and using our H-bridge cleverly, we can create something similar to a boost converter for generation at low speeds. Now, to the portion of my audience that aren't familiar with boost converters, and maybe some that are, that sounded like a bunch of confusing nonsense. So let's talk about it a little less fancy. Let's start by asking, what is our primary issue? As we said, when our motor's turning at low speeds, we cannot generate electrical current from rotation because our back EMF cannot overcome the supply voltage. So the fundamental problem here is that the voltage we have to overcome is too high. Well, what if we took the supply voltage out of the question? If instead of connecting one side of the motor to high and the other to ground, what if we just shorted our motor leads together via ground? Well, now the electrical system dynamics have changed, and our current is simply equal to the back EMF divided by resistance, meaning that even at very low speeds, we can generate a current. And at this point, the astute among you will be saying, cool, we can generate a current at low speeds now, but we're not capturing any energy back. And you're right. In this configuration, we're just driving current in a loop and it's not going back into our supply. However, we can use the facts that A, motors have inductance, and B, current cannot instantly stop when running through an inductor in order to drive current back into the supply. Essentially, we'll PWM the MOSFETs of this system such that for some portion of the PWM's period, the leads of the motor are shorted together so that the motor's rotation can build up a current. Then we will switch our FETs such that this current, which must decay smoothly, has to run back into our supply. It's worth noting here that the way you configure this second part of the period will vary depending on what your switching scheme is and potentially with how fast your motor is turning. It's also worth noting that depending on circumstances, it's sometimes possible to regenerate more power using this method than could be achieved with the non-PWM method described earlier, even if your motor is rotating quickly enough to allow for either. This may seem confusing, but it is possible as, while the PWM method will have lower efficiency, it's able to operate with higher currents and thus can take more total power out of the mechanical system. When you're using this PWM method of regeneration, optimizing the energy you recapture becomes a balancing act between your PWM period and your motor's rotation rate. The more of the PWM period you spend with the motor leads shorted together, the more current you're able to build up in the inductance. However, this also leaves you with less of the period to have your current running back into the supply. So, if your primary goal is the reclaiming of kinetic energy, your ideal PWM period will be a function of your rotation rate, your motor's characteristics, and your supply voltage. However, with regeneration, electrical energy is really only half the story. The other important side that needs to be considered is the mechanical system, because, as we said earlier, the torque produced in the motor is approximately linear with the current running through the motor's coils. And by modifying your PWM period, you modify this current, varying the braking torque produced. So, if you're just maximizing the energy you're reclaiming, you may be producing non-optimal torques within your motor. But when a driver presses the brake pedal in their car, more often than not, producing the right braking torque is more important than optimizing the energy reclaimed. And this is what ultimately brings us back to answering the question we asked at the beginning of all this. Why are your car's brake pads getting worn out? Well, it turns out that the non-intuitive answer is that the reason your car is using your brake pads so much is that it is optimizing its regeneration. You see, By using a parallel mechanical brake, it allows the motor system to optimize its regeneration of power without also having to take on the challenge of producing the ideal torque. So, the system uses its regenerative braking and the optimal configuration to harvest kinetic energy, and then it uses its mechanical brake to supplement the resistance provided so that you stop where you need to. The seemingly paradoxical takeaway is that in some circumstances, essentially throwing some of your kinetic energy away via friction can actually allow you to recapture more energy than you would be able to do otherwise. And this isn't just true for cars. For any system which has regenerative braking, having a mechanical system in parallel which can dissipate some of the kinetic energy and supplement the motor's braking allows the motor to harvest more energy from the world around it. And I think that's pretty neat. Anyway, I hope you learned something interesting today, and as always, thank you for watching.